You see that there's the bromide here, but somehow what happened was we added those 4 carbon instead of bromine. So these 4 carbon butyl groups has to come in and replace the bromine. So that is basically what has to happen. What would you use to make this one happen? That's clearly a substitution reaction, right? And then bromine goes and something goes in. I would say that that's kind of a nucleophilic substitution reactions, probably a SN2 reaction, right? And we need a nucleophile with the 4 carbons. So what carbon nucleophile with the 4 carbons? Like a butyl anion. This is the anion, but yeah, that's kind of unstable, but we can still make it. By the butyl bromide, you treat the butyl metal, and you can make the butyl anion. And butyl lithium, I'm sorry. And that is basically taking this carbon, take the bromine groups out, and that is just nothing but SN2 reactions. And this is a allylic system, so that reaction will happen pretty fast, right? So this is pretty similar. We got bromine here, and basically 2 bromopropane, and then that's a product. So I would say these 3 carbon is a product of those 3 carbons. So those 4 carbon is added, right, by the reactions. So for the same way, we can think about what about making those anion there, make some attack SN2, kick these things out, and make this product. That's the approach we took for the previous question, right? So it's kind of the same thing. I just break the molecule into the pieces. That's coming from this. This must be the nucleophile. So I place a negative charge there. So that's the anion, the carbon ion nucleophile. That makes an attack, kicks it out the bromide, better make the products. Are you guys happy to see this? Or are you okay with this answer? I mean, previous one, we didn't question that was what happens in the mass answer, we take it and we move on. But this one, would you take it as an answer? There's something to be considered, something that you already know, but you probably forgot. So let me refresh your memory. SN2 reaction, what is sensitive about? Substitution, right? Previous ones are allylic bromide. It's a primary bromide in allylic position. There's no way you could have elimination done. But this one's a different because there's a proton there. So if that acting as a base, pick up this proton, double bond's going to be created, that goes out, it's an E2 elimination reactance. So E2 is potentially happen with the SN2. Which way will it happen? I don't know. I mean, this is secondary. Secondaries are always difficult to predict. And then, is this a small nucleophile? If the nucleophiles are small, then probably SN2 might be better. But this is a kind of a little, I would say small. That's kind of some size. I don't think it's a big either. But so it's hard to say. SN2 could happen. I'm not saying that this will never happen. This could happen, but that will happen too. There's another issue. What else could it be? Yeah, exactly. There's a double bond to this. What that means is this carbon ion is also make a resonance structures. This can attack, but that can also make an attack. But think about if that makes an attack, then you make a different product. You're making things that we're supposed to make. You make different ones. And obviously, this looks like a little bigger nucleophile than that one because there's a primary position, the secondary position. This would probably go for the deprotonation and then make the E2 elimination probably better, in my opinion. So that would probably make this. That would be really, really minor products, in my opinion. And this will form and that will form. This is going to be kind of crazy. So, yeah, if you, I mean, that's the simplest answer, but things doesn't always happen that way. Then that's what we're going to do. With this approach, have multiple problems. Then what we could do, we can switch, right? The bromide can be changed to the carbon ion by treating like the lithium or the, make a grignard if you want to. So we can always change that to that base of, carbon ion. Then you need that as an alkyl bromide, which it is. So this carbon ion makes an attack. It's a allylic system, so this goes out. I think this can be prepared much better than the way we do it up here. Sure.
That you used to get rid of the broken previously, or that lithium?
Yeah, that's lithium.
Okay.
Yeah. Because I treat the lithium metal, and then so you get the organic lithium there, and that's a carbon ion, makes an attack, a lithium bromide, and kicks it out, you can make that. So that seems to be the product, right? I like to say that, this is a probably better way than the way before. I was kind of not sure whether I should talk about this or not. So if you prefer, you can forget about what I was going to say. What else could happen is that this actually attack this double bond, this pi system goes here and kicks it up. This is happen especially those type of allylic bromide. It happened, I've seen it multiple places. This is kind of another thing that could happen. If it does, then you're gonna have a different product. So that is another issue. So this way you have an issue, that way you have an issue. What are you gonna do? Heating up is not the next. So this is what I'd like to remind you. There's another thing you could do. You got lithium, organic lithium prepared, you prepare the cuprate. I'm pretty sure you forgot about this thing. That cuprates, and then this allylic bromide will capture only makes that. It will never rearrange those diethyl cuprate specialty is a make of carbon bonds, not going through the carbon ion, not going through the radical, it's just metal catalyzed reaction that we can't too complicated to talk about it, but they are much more free of the other problem. So cuprates is a really good at making those carbon bonds together. So I'm pretty sure that you forgot all those things. That this is kind of moment to refresh your memory. What that means is some of those all reactions that you kind of forget about when we came on one. Now you need to be back. So you probably have to study those things again beyond today. Thank you, everyone.